Welcome, students. We are going to discuss about step functions. Um, so why is the Laplace transform useful? So far, whatever we have done until now in this course, we could have done it directly by solving from techniques of chapter 3, right? So so far we have done the following. We had AU double prime plus BU prime plus CU equals to G of t. And this G of t was continuous, right? However, Laplace transforms are most useful for solving differential equations where the right hand side is is piecewise continuous function. Yeah. So in this section, we'll consider Laplace transform of such functions. Okay. So for that, we'll define few functions. So the first function, which is piecewise continuous function, is called Heaviside function or unit step function. So we need a notation for it. So we'll denote it by ut of c. And the idea is it's a step function. So what it is, it's 0 if t is less than c, and 1 if t is greater than equal to c. So if we draw it, this is how it will look like. So we have, it is at c. So this is your c. Before c, it is all 0, right? So it is 0. So before c, it's 0. However, after c, it is going to be 1. So after c, it is 1, yeah, including the c itself. So this value is 1 here. So this is an example of a unit step function. It goes on in this direction forever. So now, next interesting function, again a piecewise function, is what is called as indicator function. So we'll denote it by h of t. So let 0 be less than a less than b, then h of t, which is indicator function of this, you can, h of t is 1 if a lies in this open interval a to b, and 0 otherwise. So that is if t is less than a or t is greater than equal to b. Yeah. So this is an indicator function. So this is an indicator function for interval ab, and some text also refer this as the indicator function, same as h. All right. So if I draw this, this is how it's going to look like. So you have a to b. So it is indicator for a to b, a closed. So we have a closed, it's 1. B, it's 1 with a hole, and otherwise it is again given by the following. So let me just color this up so that it's clear. So if this is my axis, then the indicator function will be, it's 1 here, and it's 0 otherwise, right? So on this part, it's going to be with a hole, with a dot. So this is how my indicator function looks like. Okay, so it's an indicator for the interval AB. Now we can write the indicator function in terms of step function as well. So recall, if I have indicator function ht, which is 1, if a is less than equal to t, which is strictly less than b, and 0 otherwise, which is same as saying t less than a or t greater than equal to b, greater than equal to b. So note that you can write h of t equals to u a minus ub of t. Let's see that why. So first graph is going to be ua, which is a included. So this is graph of ua of t. So if you look at this, the graph looks like it is constant 0 before a, and after a it is 1. Now let's look at ub, which is going to be, so ub is after b it is 1, but before b it is what? It is 0. So it's 0, right? So your a is here, your b is here. So the idea is when you do UA, you start from UA. So if you look at UA, the idea is here at UA, the value is, so at UA minus UB is 1. So it's all the way 1 here, 1, 1, 1, 1, 1. But at this point, it becomes what? 0. So at B, it becomes 0, and then thereafter it becomes 0 as well. So therefore, you can see that this is what UA minus UB is. So we can also write it down to demystify it a bit. You can have UAT minus UB of t. Now the interesting points where things are really happening is at A. So when t is less than A, when A is less than equal to t less than B, and then when t is greater than equal to B. So now let's see what is happening. So UA minus UB is going to be 0 minus 0. So we have 0 minus 0, which is 1. So 0 minus 0, which is 0. My bad, not 1. Here it will be in from A to B, UA is 1. This is 1, but this one is 0. So we get 1 minus 0, which is 1. And then the next significant after t greater than equal to b, both are 1. So 1 minus 1 is 0. Okay. So now we want to talk about Laplace transform of a unit step function and also of the Laplace transform of the indicator function. So why are we studying this? Because we will build our piecewise function out of these two functions, okay? Or in particular, we'll build our piecewise function from the unit step function, okay? So let's study the Laplace transform of the unit step function UC of t. So again, by definition, so this is UC of t evaluated at s is going to be 0 to infinity e to the power minus st uc of t dt. Now you can break it into two parts from 0 to c e to the power minus s uc of t dt plus c to infinity e to the power minus st uc of t dt. Now note that this is 0 in this 0 to c, right? uc of t is 0. So this becomes e to the power minus st times 1, because uc of c is then 1 here. So we get integral c to infinity of uc of t, so it becomes 1 dt. And now that is going to be e to the power minus st over minus s 0 to infinity. Now note that when I'm doing the limits, really, as for the infinity, I should, when I write it down completely step by step, then I should use limit, all right? But however, when you do this computation, you can see that u to the power minus cs over s, and you have c greater than, so s greater than 0, my bad. So this can be seen in formula table, formula 12 of table in section 2.6.2. Now let's find out the Laplace function of the indicator function. So we have h of t equals to uat minus ub of t. Now note that even though h does not indicate this, we will reserve this notation h for ua minus ub. So our idea of interval is in some sense fixed here, all right? Okay, so now if you use Laplace transform of h of t of s is same as Laplace transform of ua t of s minus Laplace transform of ub t of s. Yeah, the reason is linearity of Laplace transform. Laplace transform. So therefore, this is, we have already computed this here. So we get this is e to the power minus as by s minus e to the power minus bs by s, or rather e to the power minus as e to the power minus bs over s. So this is the Laplace transform of the indicator function. Now comes the idea that we have a delayed forcing function. Again, the idea is, if you remember, you have bu prime plus cu equals to g of t. And we want to talk about forcing functions where g of t is not continuous anymore. Yeah. So let f of t be a function. Let's define and let g of t be 0 if t is less than c, and f of t minus c if t is greater than equal to c. Yeah, so this so if you look at it in differential equation perspective, in a differential equation problem, this corresponds to to force equal to f applied at the beginning at the delayed time t equals to c. So in some sense, you're not starting to apply the function until time t equals to c. And when t equals to c, you are applying f of 0. So it's the same for function f of t you're applying on your differential equation, but but it is applied after a delay of of basically c t equals to c time. Okay. Now we want to discuss about Laplace transform of the delayed forcing function g of t. Because recall when we did a problem on last time on Laplace transform in the last lecture, we applied Laplace transform on both sides. So this side, the left-hand side is pretty easy to deal with. It's the right-hand side where the function becomes interesting if it is a discontinuous function. So that is what we are trying to deal with at the moment. Okay, so now suppose your g of t is ut times f of t minus c. The forcing function is delayed, and now we want to find out Laplace transform of this. So this is going to be ut of this times f of t minus c evaluated at this. And again, let's write down the definition first. So the plain definition is 0 to infinity e to the power minus st ut f of t minus c dt. Now note that this ut of c will force everything before c to be 0 and after c it is 1, right? So I can rewrite this equation as c to infinity e to the power minus st. After c this is 1, so I'm gonna not write anything. I have f of t minus c dt. Now let's try to understand how to simplify this. So I'll do a substitution here. Let u be t minus c. Then we get du equals to dt, and we get when u is c, so when t is c implies u equals to 0, and if t goes to infinity, u also goes to infinity, right? So this integral will change to 0 to infinity e to the power. Now instead of s, so I'll have s as it is. Instead of t, I have u plus c. So this will be u plus c times f of u du. Now we can break this into two parts. So 0 to infinity e to the power minus su times e to the power minus sc f of u du. Now note that this s e to the power minus sc does not depend on u, so that can be pulled out. So we have e to the power minus sc 0 to infinity e to the power minus su f of u du, and then this is same as Laplace transform of, so this is going to be e to the power minus sc Laplace transform of f of t, right, evaluated as, because f of u du is same as f of t dt. So now you notice the following. So if you have u c t f of t minus c, it becomes same as e to the power minus sc Laplace transform of this. Okay, so this is formula 13. This is formula 13 in the table in section 6.2. So now let's find Laplace transform of some more piecewise function. So consider the following. F of t is 1 if 0 less than t less than equal to 1. It's 1 plus t minus 1 square if t is greater than 1. So now we want to find Laplace transform of this. So, well, one way is to directly apply the formula and work it out in a brute force way. In other way, you can basically see that this function can be converted into following form. So this function can be written as 1 plus constant function 1 for all t plus 0 to 0 when t is between 0 and 1, and t minus 1 square t greater than 1. Now the reason for doing that is now you can bring in the step function in the game. So we have u1 of t minus 1 square. So now we can apply the Laplace transform. So therefore Laplace transform of f of t evaluated as is going to be Laplace transform of 1 plus Laplace transform of u1 of t minus 1 square s. Now Laplace transform of 1 is 1 over s. This is going to be e to the power. So uc is e to the power minus sc. So this is going to be e to the power minus s times 1 times Laplace transform of what? You would then bring it back, right? So you had t minus 1, t minus c becomes t. So this is the way, this is a standard way to bring it back to going to be Laplace transform of t square at s, and that is, so note that Laplace transform of t to the power n is n factorial upon s to the power n plus 1. Yeah, this was true when n belongs to n, right? So when n belongs to n, this is what it is. So here we'll have 1 by s plus e to the power minus s. So it will be t, so 2 factorial, so which is 2 divided by s to the power 2 plus 1, so s cube. So this is the Laplace transform of that. Now let's work on this problem. Laplace transform of, find Laplace inverse of g of s, which is given by 1 upon s minus 2s plus 3. So first thing is we'll complete the square. So we get g of s equals to 1 upon s square minus 2s plus 1 plus 2, which is same as 1 upon s minus 1 square plus 2, which is same as f of s minus 1, right? You can think about it as a function of f of s minus 1 with f of s equals to 1 upon s square plus 2. Yeah, which can be seen as root 2 by root 2 times 1 upon s square plus 2. Now, why are we doing this? Because here we are thinking about, the Laplace of sine of at s is a upon s square plus a square. So that's why I multiplied it on top by 2 because this term, for example, can also be replaced as square root of 2 square. So this connection really. So therefore we have Laplace inverse of g of s is Laplace inverse of f of s minus 1. Now, what is Laplace inverse of f of s minus 1? It's going to be, so from here you can read that Laplace inverse is going to be f of s minus 1 will be f of e to the power t. So this is going to be e to the power t times Laplace inverse of f of s. And now we already know what is Laplace inverse of, this is the f of s. Laplace inverse of that is take root 1 by root 2 common because it's a constant, comes out of the Laplace transform, and Laplace inverse of root 2, I'll write that here, Laplace inverse of root 2 upon s square plus square root of 2 square is sine of root 2 t. So this will become sine, so e to the power t, 1 by root 2 comes out, sine of root 2 t. So therefore we get Laplace inverse of 1 upon s square minus 2s plus 3 is e to the power t by root 2 sine of root 2 t. So that solves the problem. Yeah, so here you can see that we used, yeah, here we used, so s minus 1 square, we used this formula here. Yeah, okay, all right, thank you for your attention.